The Earth has a heartbeat, and for Japan, that beat is a constant, terrifying tremor, a relentless reminder that they live on borrowed time. Sitting squarely on the Pacific Ring of Fire, the nation is the site of nearly 20% of the world's most powerful earthquakes. For any other country, this constant geological violence might be a death sentence for its urban ambitions, condemning its cities to perpetual anxiety and inevitable ruin. But for Japan, the threat has simply become the ultimate, most profound design challenge. They don't just build to survive a quake, they engineer to defy it, creating megastructures that perform the impossible by literally dancing with the seismic forces. They transform towering skyscrapers from rigid targets into fluid, adaptable partners of the Earth's movements. This is the incredible high-stakes story of how Japan transformed a devastating geological threat into the greatest catalyst for architectural and civil engineering innovation the world has ever seen, demanding nothing less than human genius to beat the Earth at its own game. Japan's obsession with seismic resilience is not academic. It is forged entirely in tragedy and fire. The turning point came in 1923 with the Great Kanto earthquake, an unimaginable catastrophe that devastated Tokyo and Yokohama, killing over 100,000 people and leveling entire districts. The trauma of that disaster, where older, weaker structures were consumed by fire or collapsed into rubble, led to the first major reforms of building codes. For decades after, construction was governed by the Taishin, or Old Seismic Standard, which focused narrowly on working stress design, essentially aiming for buildings to remain intact under routine stress, but having little capacity for extreme events. The true modern revolution, however, began after the 1981 Shin Taishin, or New Seismic Design Standard, which dramatically raised the technical bar. This new law ushered in ultimate strength design, a philosophy that demanded buildings must withstand a rare, severe earthquake, specifically one generating a maximum ground velocity of 25 cm per second, without catastrophic, life-threatening collapse. This mandate fundamentally changed the geometry and materials used in every major project across the country. Yet, this ambition was soon tested and brutally found wanting in 1995 when the Great Hanshin earthquake struck Kobe. The unprecedented ground acceleration and the unique shallow depth of the tremor brutally exposed critical flaws in the older structural stock built before the 1981 revisions, leading to the infamous pancake collapse of elevated highways and the brutal shearing of thousands of older reinforced concrete columns. It was a chilling, undeniable wake-up call, demonstrating that an existing building stock was a massive, lethal liability. The tragic, costly lessons learned in Kobe, the stark realization that mere static strength was inadequate, spurred engineers to pivot radically. The focus shifted permanently from mere quake resistance, building stronger to avoid breaking, to sophisticated isolation and damping, a revolutionary and nuanced philosophy of accommodating and neutralizing the Earth's fury rather than rigidly confronting it head-on. The most visually stunning and conceptually crazy engineering solution Japan pioneered is base isolation, known locally as menshin. Instead of rigidly fighting the Earth's movement, these structures choose to separate themselves from it. Imagine a massive skyscraper resting not directly on its foundation, but on a colossal layer cake of flexible bearings, alternating layers of lead, steel plates, and high-damping rubber. When an earthquake hits, the ground beneath the building can move violently, but the rubber bearings absorb the lateral energy and slide, extending the building's natural sway period to several seconds. This decoupling effect reduces the shaking experienced by the structure and its occupants by up to 80%. Thousands of buildings now employ this technique, transforming them from static targets into dynamic dancers on a field of rubber. Taking this concept one step further, companies like AirDanshin have even developed a system for smaller homes, where a seismic sensor triggers an air compressor, momentarily levitating the entire house a few centimeters above its foundation, on a cushion of air to completely detach it from the ground motion. For the modern super-tall skyscrapers like the Mori JP Tower and Azabudai Hills, or the iconic Tokyo Skytree, base isolation alone is insufficient, especially against the long-period seismic waves that can travel vast distances and cause high-rises to sway dangerously. This is where damping technology, seismic, takes over. These are the internal organs that regulate the building's kinetic energy. Oil dampers, essentially industrial-sized shock absorbers, are installed between structural beams and work by converting kinetic energy into heat. Even more spectacular are the tuned mass dampers, TMDs. In the Tokyo Skytree, a massive concrete core inspired by the Shinbashira central pillar, found in ancient Japanese pagodas, acts as a dynamic counterweight. This core is intentionally built to be slightly separate from the surrounding steel lattice and connected by enormous dampers. When the tower sways one way, the independent core is engineered to sway the opposite way, neutralizing the energy and ensuring the 634-meter structure remains stable. This combination of ancient wisdom and hyper-modern engineering is what allows Japan's skyscrapers to survive a magnitude 9.0 event with minimal internal damage. While Japan's structural engineering of buildings is a global marvel, its mega projects to protect against the secondary, more destructive force of earthquakes, the tsunami, remain deeply controversial. Following the catastrophic 2011 Great East Japan earthquake and tsunami, which tragically overwhelmed existing defenses, the Japanese government embarked on a massive $12 billion project to construct nearly 400 kilometers of new, colossal seawalls. In some areas, these concrete barriers rise up to 14.7 meters, essentially creating a massive gray shield between the Pacific Ocean and coastal communities. The controversy surrounding this project is profound. Firstly, there is the question of false security. The 2011 tsunami proved that even the largest walls can be overtopped, and some experts argue these new walls simply create a higher, more devastating water surge when they fail, delaying evacuation rather than guaranteeing safety. Secondly, the environmental and social cost is immense. These walls have irrevocably altered the coastal landscape, blocking views of the sea, disrupting delicate marine ecosystems, and fundamentally changing the way communities interact with the ocean that has defined their culture for centuries. Critics argue the money would have been better spent on retreat, land elevation, and comprehensive early warning and evacuation systems, rather than fighting an ultimately unbeatable force of nature with concrete alone. Despite the ongoing debates over the ethics and efficacy of coastal defense, Japan's relentless drive for structural resilience continues to push the boundaries of materials, science, computational design, and architectural geometry. Engineers are already working on next-generation systems, including smart dampers linked to AI-driven earthquake early warning systems that can adjust their properties in real time, and structures designed with self-healing concrete that can repair microscopic fissures instantly. The reality is that Japan is not just building earthquake-proof structures, it is building a fundamentally new, deeply resilient relationship between humanity and its planet, one where the greatest, most unavoidable natural threats are met, not with resignation or retreat, but with a complex, innovative, and deeply committed vision of collective survival. They build for the inevitable, ensuring that when the Earth next shifts and unleashes its colossal energy, their megastructures will not fall, but simply settle back down, having absorbed the shock, remaining stable, and standing ready for the next tremor. Japan's architectural genius is a powerful testament to the idea that human potential shines brightest when faced with the greatest adversity, defining the future of engineering for a shaking world.